we have looked into the design and the performance of both uniform and non-uniform PDF optimized quantizer, that is Lloyd-Max quantizer. In the case of uniform quantizer, we have seen that the decision boundaries or the boundary values and the reconstruction levels are equally spaced. That is, the size of the quantization interval is the same. However, in the case of non-uniform PDF optimized quantizer, that is Lloyd-Max quantizer, both the decision boundaries and the reconstruction levels are unequally spaced. That is, the quantization interval is smaller in those regions that have more probability mass. Implementation of a non-uniform PDF optimized quantizer is much more difficult than a uniform quantizer, but also mean square quantization error is lesser in the case of a non-uniform PDF optimized quantizer compared to uniform quantizer. There is another approach to achieve the similar beneficial result of lesser mean square quantization error of a non-uniform quantizer. Instead of making the quantization interval small, we could make the region in which the input lies with high probability large. That is, we could expand or stretch the region in which the input lands with high probability in proportion to the probability with which the input lands in this high probability region. This is the main idea behind companded quantization. The companded quantization can be represented by the following block diagram. First, the input is mapped through a compressor function. The compressor function task is to expand or stretch the high probability regions close to the origin and compress the low probability regions away from the origin. The net effect of this is that regions which are close to the origin in the input to the compressor now occupy a greater fraction of the total region in the output of the compressor. Now, the output of the compressor is uniformly quantized and the quantized value is transformed via an expander function which is the inverse of the compressor function. The net effect of this whole process is the same as using a non-uniform quantizer. This is known as companded quantization. Now, before we look into the mathematics of companded quantization, let us try to get the feel of this process with the help of a simple example. Let us assume a source whose output can be modeled as a random variable, and this random variable takes values in the interval -4 to +4. Let us assume that this random variable has non-uniform PDF with higher probability mass near the origin than away from it. Let us use a 8 level mid-rise quantizer of the form shown in the figure here. So, this is the quantizer input output mapping for a mid-rise quantizer. Quantization step size is 1, and reconstruction levels are the midpoints of this interval. So, first let us try to flatten out the non-uniform PDF using the following compressor and expander. Which together is known as Companded. The compressor function is shown here graphically, and mathematically it is C x is equal to two x if x lies between -1 and +1, and it is equal to 2 x by 3 plus 4 by 3 if x is greater than 1, that is this, and it is equal to 2 x by 3 minus 4 by 3 if x is less than -1, it is this. So, this is the compressor function or compressor mapping, and the expander mapping or the expander function is shown here in terms of C inverse x, and the characteristic can be written as C inverse x is equal to x by 2 if x lies between -2 and +2, that is this region, and it is equal to 3 x by 2 minus 2 if x is greater than 2, that is this line, and finally, it is equal to 3 x by 2 plus 2 if x is less than -2, that is this line. So, between compressor and the expander, we have the uniform quantizer, and that is shown here. We have the range between -4 +4 with 8 levels. So, we denote -4, -3, -2 and so on as boundary values, and 3.5, 2.5, 1.5 as the reconstruction levels. Now, let us study how this compressor and expander functions affect the quantization error both near and far from the origin. So, let us say we have input as 0.9. Now, if we directly quantize this without the compounder, then the output of the uniform quantizer would be 0.5, because 0.9 lies between 0 and 1, and the error in this case would be 0.4. Now, if the same input was passed through a compounder, then let us see the output. So, 0.9 when it passes through the compander characteristics which we just discussed, the output would be 1.8, and the output of the compressor will be fed to the uniform quantizer, whose output will be 1.5. So, the apparent error is 0.3, and then finally, the quantized value passes through the expander to give the value 0.75, and in this case the error is the difference between 0.9 and 0.75, that is 0.15. So, we see that without the compander the error is 0.4, whereas with the compander the error is 0.15. Similarly, if we take minus 0.8, this would be quantized to minus 0.5 without the compander. So, the error, absolute error would be 0.3. Now, if we pass this through a compander, the output would be minus 1.6, which when uniformly quantized will give the value of minus 1.5, and which when passes through the expander will give minus 0.75. So, the error in this case is again less, and it is equal to 0.05. Similarly, we could extend this to 0.3, this would give to 0.5, the error is 0.2, and when we pass through compressor it will give 0.6, which will be quantized to 0.5, pass through expander will give 0.25. So, the error is 0.05. Again, the error here with the compander is less than without the compander. And finally, let us take a value of 2.7, which without the compander would be quantized to 2.5. So, the absolute error is 0.2, and if we pass through the compressor, this will give us 3.13, which will be quantized to 3.5 uniformly, and when passed through the expander it will give back 3.25. In this case, the error is 0.55. So, the companded quantizer effectively works like a non-uniform quantizer with small quantization intervals in the interval between -1 to +1 and larger quantization intervals outside this interval. So, the next question is, what is the effective input output mapping for this quantizer? Now, it is easy to see that when the inputs lie in the interval between 0 and 0.5, then using the compressor it gets mapped into the interval between 0 to 1, and when this output of the compressor is passed through a uniform quantizer, it is quantized to output value of 0.5, and this when it passes through the expander it gives us the reconstruction level of 0.25. So, effectively the input between the range 0 to 0.5 gets mapped to 0.25. Similarly, the input between the interval 0.5 to 1 on passing through the compressor get mapped to the region between 1 and 2, and this gets quantized to 1.5, and the output of the expander is 0.75. So, again effectively the interval between 0.5 to 1 gets mapped to 0.75. So, the effective quantizer input output map is shown in the figure here. The values between 0 and 0.5 get mapped to 0.25, between 0.5 to 1 they get mapped to 0.75, and so on. Now, having studied this simple example, let us try to extend these concepts to a more generic input. For this, let us assume that the source output is bounded by some maximum value, let us call it as x max. Let us also assume that the number of quantization levels are high, that is, we deal with high rate quantizers. Now, with these assumptions, let us denote the distance between two boundaries of a quantizer as delta j, which is equal to b j minus b j minus 1. Now, if we assume that the number of quantization levels that is L is high enough, then the size of each quantization interval will be small, and therefore, it would be quite reasonable to assume that the PDF of the input, that is given by P x, will be essentially constant in each quantization interval. That is, we can approximate P x is equal to P x y j if x lies in the interval between b j minus 1 and b j, where y j is the reconstruction level of the interval b j minus 1 b j. So, now, we know that mean squared quantization error is given by the following expression. Now, this expression can be rewritten based on the above assumptions as follows. This comes out of the integral because of being constant, and this can be simplified as follows. The value for this expression is equal to where delta j is equal to b j minus 1. Now, for the companded quantization, if we let C x denote the compressor characteristic for a symmetric quantizer, and let C dash x denote the derivative of C x with respect to x, and let us assume that the number of quantization level, that is L, is high. Now, given this, now any general compressor mapping will look as follows. So, within the jth interval, the compressor characteristic can be approximated by a straight line, and therefore, the derivative can be approximated as C dash y j is equal to C of b j minus C of b j minus 1 divided by delta g. This is an approximation of the derivative, and from this figure we also see that C b j minus C b j minus 1, this difference is the step size of a uniform L level quantizer. Therefore, we can write C b j minus C b j minus 1 is equal to 2 x max by L. This is the step size of a uniform quantizer, where the input is bounded by x max and there are L number of levels. Therefore, with the given approximation, delta j is equal to C b j minus C b j minus 1 divided by derivative at y j is equal to 2 x max divided by L times C dash y j. Using this relationship, we can rewrite the mean square quantization error as follows: 1 by 12 summation over j equal to 1 to L delta j can be approximated by 2 x max upon L times C times y j cube. This essentially comes from this expression which we just saw some time back, and this can be rearranged as follows: and again simplified as x squared max upon 3 L squared summation over j equal to 1 to L p x y j delta j is equal to this quantity. Now, if we assume that L is high, then delta j will be small, and in that case we can replace this summation by integration as follows. So, mean squared quantization error expression reduces to this integral is known as Bennett integral after its discoverer W. R. Bennett. And this famous result is widely used to analyze quantizers. Now, if we observe mean square quantization error, it is dependent on PDF of the input to the quantizer. So, let us define C dash x as x max by beta times mod x, where beta is a constant. Now, using the Bennett integral and using this relationship, it is easy to show that mean square quantization error reduces to the following expression. which is equal to beta squared, that is a constant, divided by 3 L squared times sigma x squared. This is the variance of the input. Therefore, signal to quantization noise ratio in dB will be equal to 10 log sigma x squared by sigma q squared is equal to 10 log 3 L squared minus 20 times log beta. And this expression shows that signal to quantization noise ratio is independent of the input PDF. So, this implies that if we use a compressor characteristics which satisfies this relationship, then signal to quantization noise ratio will remain constant regardless of the input variance. Now, it is important to note that this impressive result is valid as long as the underlying assumptions used to derive this results are valid. For instance, if input variance is very small, then our assumption that the input PDF remains constant over the quantization interval will be no longer valid, or if the input variance is very large, then our assumption of the input being bounded by x max will be no longer valid. So, assuming that these assumptions are valid, we can derive the compressor characteristics as follows. We saw that C dash x is equal to x max by beta times mod x. Therefore, this on integration results into compressor characteristic given by C x is equal to x max plus alpha times log mod x by x max, where alpha is a constant. Now, for small x, C x assumes very large value. Therefore, in a practical situation, to avoid this technical difficulty, the compressor characteristic is approximated with a function which is linear around the origin and it is logarithmic away from the origin. Now, two popular practical compending characteristics are as follows. One is known as mu law compending, because the characteristic is a function of a parameter mu and it is given here, and this is the inverse characteristic, that is the expander characteristic, where signum x is equal to 1 for x greater than 0 and minus 1 for x less than 0. Mu equal to 255 is the value which is used in telephone system in North America and Japan, whereas the rest of the world use A law characteristic for companding, and that is given as follows. So, this is A law companding, where the function or characteristic is a function of the parameter A, and the typical value for A is equal to 100, and for the same A law companding, expander characteristic is specified as shown here. Now, let us take few examples to understand these concepts in a better way. Let us take the first example as follows. Consider a mu equal to 255 compander to be used with a 8 level quantizer with the output variation over plus minus 10 volt. For an input of say 0.5 volt, it is desired to find the quantization error with and without companding. So, let us try to provide the solution for this. So, let us first consider without companding and using uniform quantization. So, in this case the step size is given by to x max by L. In this case we have 2 into 10 by 8 level quantizer. So, the step size is 2.5 volts. Now, the given input 0.5 volt lies between 0 and 2.5 volt. Therefore, the first reconstruction level for the positive x is 1.25 volt. Therefore, 0.5 volt will get quantized to 1.25 volt, which implies that the quantization error will be equal to 1.25 minus 0.50 is equal to 0.75. Now, let us look at the quantization of 0.5 volt with the help of mu law compander. So, with companding, the first step is to pass it through compressor, which is equal to C x max log of 1 plus mu times So, we substitute the given values as this reduces to 4.73. So, this is the first step. The next step is to take the output of the compressor and feed it to the uniform quantizer. Now, so next step is uniform quantization. Now, 4.73 lies between 2.5 and 5, and we know that the quantization step size is 2.5. Therefore, 4.73 will get quantized to 3.75, which is the reconstruction level for the interval between 2.5 and 5, that is the average of these two values. And the final step is to take this 3.75 and pass it through the expander characteristics, which is given as C inverse x is equal to x max by mu times 1 plus mu raised to mod x by x max minus y So, this is equal to and this can be evaluated as 0.27. So, in this case the quantization error with compending absolute value is equal to 0.50, which is the input, minus the quantized value 0.27 is equal to 0.23. So, without compending we have an error of 0.75, whereas with compending we have an error of 0.23. So, this shows an advantage of compending. Now, let us look into the performance of mu law compending little more in depth, and in order to simplify our discussion, we will assume that the input to the mu law compender is normalized by x max. So, in this case we have the input which lies in the interval between -1 to +1. So, if we assume that, then in this case the quantization noise expression, that is this, reduces to where x is a normalized random variable, means x is lies between the interval -1 and +1. Now, if we assume the symmetry both for input PDF and compressor characteristic, then this expression reduces to 2 by 3 L squared and therefore, signal to quantization noise ratio is equal to input variance divided by the quantization noise, which is equal to S x divided by q squared is equal to 3 times where S x is by definition input variance and K c is by definition equal to twice the integration of input PDF divided by the squared of c dash x. So, this is a constant which is dependent on the compressor characteristic and the input PDF. So, in this case the popular mu law compending for voice telephone employs the following compressor characteristic. And therefore, c dash x is equal to mu by log 1 plus mu times 1 by 1 plus mu times mod x. The parameter mu is a large number. So, c dash x is much larger than 1 for x much smaller than 1 and c dash x is less than 1 for mod x approximately equal to 1. Therefore, in this case K c, which is equal to twice integral from 0 to 1 of p x c dash x squared is equal to twice log squared 1 plus mu by mu squared and it can be very easily shown that this expression reduces to K c is equal to log squared 1 plus mu by mu squared 1 plus 2 mu mod x plus mu squared S x, where average of mod x is equal to by definition twice and S x is the input variance, which is equal to now we need the values for average of mod x and S x to test the efficacy of mu law compending. Now, empirical results have shown that the PDF of a voice signal is reasonably modeled by Laplacian PDF of the form equal to alpha by 2 e raised to my alpha times mod x, where alpha is a constant, and in which case S x is equal to 2 by alpha squared, and average of mod x is equal to 1 by alpha is equal to square root of S x by 2. Now, unfortunately, this PDF cannot be normalized for x max less than equal to 1, but the probability of mod x being greater than 1 is less than 1% if S x is less than 0.1. Now, other voice PDF models yield about the same relationship between mod x and S x, which is the critical factor for evaluating K C. So, taking the standard value for mu equal to 255 and mod x average equal to square root of S x by 2 gives the value for K C equal to 4.73 multiplied by 10 raised to minus 4 times 1 plus 361 square root S x plus 65025 S x. Now, numerical evaluations then show that K C is less than 1 for S x less than 0.03, but more significant is the fact that S x by K C stays nearly constant over a wide range of S x. So, consequently, mu law compending for voice signal provides an essentially fixed value of signal to quantization noise ratio despite the variations of S x, the input variance among the individual talkers. Now, the figure here brings out this desirable feature by plotting signal to quantization noise ratio in dB versus input variance in dB with and without the compending when L is equal to 256. From this figure, it is clear that there is a considerable compending improvement for S x less than minus 20 dB. So, in the design of a quantizer, there are three important issues. These are: first, selection of decision boundaries or boundary values; second, selection of reconstruction levels; and third, selection of code words. In our study so far, we have assumed fixed length coding for the given number of quantization levels of a quantizer. Now, if this is the case, then selection of code word is not an important issue, and therefore, we have only considered the selection of decision boundaries and selection of reconstruction levels with the constraint of minimizing the mean squared quantization error. But now, if we relax this constraint of fixed length coding, and deploy variable length coding, then the selection of code word becomes an important issue. It will be beneficial to design the quantizer wherein we can incorporate the entropy of the output of the quantizer, because this will decide the rate of the quantizer. So, in the next class we will look into the entropy constrained quantization.